Hello, my name is Amir and I will present layer folding, a network optimization method me and my colleagues developed and researched at Samsung Israel R&D Center. Layer folding is a method of reducing a pre-trained neural network's depth. While there are many works for reducing the size of a given network, most focus on reducing flops or channels, occasionally removing an entire layer as a byproduct. However, depth is highly correlated with latency, especially on edge devices. This motivates us to develop a method for depth reduction specifically, a method which is inherently different than existing methods to reduce the number of channels. Neural networks' building blocks are mostly linear. This is especially true for networks that need to run on edge devices and do not use advanced blocks, such as transformers. In order to break the linearity of the network, activations are used between layers. If we were able to remove an activation, we would get a sequence of linear layers, which can be merged into a single linear operation, as known from basic linear algebra. This holds true even when residual connection and batch norm layers are added. So, as we see, removing activations allows to reduce the depth of the network. Please note that merging convolutions with kernel size larger than 1 gives a single convolution with larger kernel. Yet the larger kernel is often more efficient on edge devices due to lower memory bandwidth and higher parallelism. Furthermore, in most popular mobile CNN architectures such as MobileNet and EfficientNet, the merged kernel might actually be smaller. Our method for removing activations is as follows. For each activation sigma, we define its learnable parametric activation counterpart. Here we can see the example for parametric ReLU. Alpha is a learnable parameter initialized as 0. For alpha equals 0, we get the original activation sigma. For alpha equals 1, we get the identity, which means that activation has been removed. During training, we want to encourage alpha to become 1 using an auxiliary loss. For each activation, we use the following loss, usually with p equals 2. This loss encourages each alpha to become 1. As our final network should not have new operations such as parametric ReLU, the power p ensures that alpha values near 1 will not be sustained during training. As you can see in this graph, the final value for each alpha is either 0 or 1. More on this can be found in the main paper. We've tested our method on several variants of MobileNet v2 and also on EfficientNet Lite. These networks are popular options for edge devices, which were designed with efficiency in mind in the first place. Using layer folding, we were able to achieve latency reduction with minimal impact on accuracy. In the main paper, we also demonstrate how this method can be used in tandem with filter pruning. We also performed extensive experiments on other common architectures such as ResNet and VGG on the CIFAR datasets. We demonstrate how hyperparameter tuning allows to optimize the accuracy-depth trade-off according to the researcher's needs. For example, we show that the depth of ResNet 56 for CIFAR can be cut by half with no accuracy degradation, or reduced to 10 layers while maintaining over 90% accuracy. We believe our findings can promote foundational neural architecture design and theoretical understanding on the required depth of a neural network for specific tasks. More on this can be found in the main paper. This was a brief overview of our work. For more information, please see the main paper and our website. Thank you.